student at Dalhousie University in Halifax, Nova Scotia. And my relatively simple title is Understanding the Effects of Human-Generated Aerosols on Precipitation. And this is work that I did with Dr. Stephanie Gagné and Dr. Jeffrey Pierce. So aerosols are fine particles that are suspended in the atmosphere. They can act as CCN, or cloud condensation nuclei. And they have a diameter of around 10 nanometers. So if the relative humidity is above 100%, they can be activated and they can form into a small cloud droplet. More water will condense onto this droplet, forming a larger droplet here. And this has a diameter of around 20 microns. At this point, it becomes too heavy and will start to fall through the cloud, coalescing with other smaller droplets, getting larger and larger and larger until it reaches the size of a drizzle drop, which is a diameter of about 100 microns. And this can reach the ground as precipitation. So with all else constant, an initially low number of CCN will yield a low number of cloud droplets with a larger droplet diameter, and this is due to more water being spread out over a smaller amount of aerosols. And this will lead to more drizzle. Whereas an initially high number of CCN will yield a high number of cloud droplets with a smaller droplet diameter, and this will give less drizzle. And this is called the lifetime effect because clouds that have higher amounts of CCN will rain less and therefore will have a longer lifetime. So in 2003, there was a measurement campaign known as SOLAS, or the Surface Ocean Lower Atmosphere Study. And what they did was take a Convair CP580 plane from the 1950s and flew it through a whole bunch of clouds around Atlantic Canada. And I just have this picture to show kind of how archaic the flight controls were when they were doing this, since the plane is about 60 years old. And it's pretty appropriate that this picture shows them flying through clouds. So here's a plot showing the location of the 10 clouds that were measured during this campaign. Apologies to those from UP guys, since the base math portion of Python doesn't think that PEI exists. So I focused on this cloud here, cloud number 2. Here's sort of a zoomed in shot of it. It's just off the southern coast of Nova Scotia. This next graph I made mostly because it looks pretty neat, but it also shows the flight path of the airplane. So you can see that they took measurements like through vertical profiles. They took measurements above the cloud, below the cloud, and within the cloud. So when they flew through the cloud, what did they measure? Well, they measured a whole bunch of size distributions. They measured cloud droplet, aerosol, and precipitation size distributions, as well as liquid water content and a whole bunch of other useful data. So here's a picture of an infrared satellite photo, I should say, taken about 2 hours before the measurement campaign. You can see that where the red circle is, that's where that cloud number 2 was. And it's sort of a darkish gray, and this indicates that it's sort of a low-level cloud. And that is a good thing to hear because during the measurement campaign, they saw low-level stratus clouds. So it's good that it matches up. On the way to Vancouver to this conference, we took off from the Halifax airport, and we flew through some low-level stratus clouds. So that looked out. So now you can kind of see what these clouds look like. They sort of expand off to infinity, it looks like, and they're sort of flat on the top. So I'll just quickly talk about the large-scale dynamics of this cloud. This is a plot made using high split, and this is a back trajectory model. And what it shows is that warmer air from the continental United States mixed with cooler air from the Atlantic Ocean, and this is how the cloud actually formed. Why it formed, I can explain this map. So vapor pressure is on the y-axis, temperature is on the x, and the red line is the saturation vapor pressure of water. So any point on that line has a relative humidity of 100%. Anything above is greater than 100%. Anything below is under 100%. So for the case of my cloud, we have warm air from the continental United States mixing with cooler air from the Atlantic Ocean. Since these behave as ideal gases, you can just draw a straight line in between. And so let's say they mix at a 50% ratio. The middle point of this line is the new relative humidity of the air mass. So it's pretty neat that two air masses that have an RH below 100% mix and form a new air mass that can create a cloud. And so once the cloud is formed, there's cloud top cooling. So the water at the top of the cloud is warmer than the air above it. So this creates dense air left to sink, which causes turbulence in the boundary layer, and this enhances mixing and it thickens the cloud. So now that we know all this about the cloud, I tried to model using SAM, or the System for Atmospheric Modeling. This was developed by Murat Karutnov. I used a resolution of about 100 by 100 by 30 meters. I used a simulation time of around 4 days. I employed nudging, and there was some spin up involved, and I'll explain what those two are in new slides. So when you run this model, you need some input parameters, one of them being surface temperature, and this is just a plot for the time the measurement was taken of what the surface temperature is. In this case, it's about 290 degrees Kelvin. So I threw that in the model and set it as a constant with the surface temperature. It's also important to have an initial aerosol distribution, so that's what we want to study. So the measurements were taken beneath the cloud. I fit the sort of, it's called the aerosol distribution. I fit that and threw the parameters into SAM. It's also important to have some initial soundings. This is just an example with altitude on the y-axis and relative humidity on the x, that when they measured the cloud, they knew what the top and bottom were, and that's right where the relative humidity is its maximum, so that makes sense. So when you run this model, you get outputs. An example, this is one of the outputs you can get with altitude on the y-axis, time on the x-axis, and the colors here represent the cloud droplet number concentration, so the amount of cloud droplets percentage cubed. I can use this to explain spin up. So spin up is the time it takes for the model to reach a statistical equilibrium. In this case, it looks like it takes about a whole simulation day to reach this pseudo-steady state. And I can also explain nudging. Nudging is when the model's output is sort of slightly forced to match that of what we want. And I only use this because during the campaign, they saw that the free troposphere had a constant supply of warm dry air. So I only nudged the portion right here, and just so that it had a constant supply of warm dry air. Another example of an output we can get is three-dimensional. This is just here to show us the top and the bottom. These are the outputs that I use most often. During the campaign, they took vertical profiles, and with this simulation, I can take about 10,000 vertical profiles per time step. So I was able to do statistics on those and compare it to what was measured. So this sort of shows just doing a vertical profile, so going sort of virtually flying through this cloud. So now I'm going to compare the model to the data that we have. Here, I'll explain how to sort of read this graph before I'll get deep into it. These black solid lines represent the measurements that were made during the campaign. And the colors represent the model's output. So I said I took about 10,000 vertical profiles, so I can do statistics on those. So the solid color line is the median for each one. The shaded region are the first and third quartiles, and the dashed lines are the 5th and 95th percentiles. So for liquid water content, to start off, it matches pretty nicely with what the measurements say. Same goes for the droplet number concentration. And even the amount of rain. It's sort of wonky, but that's sort of to be expected with the rain, since it's sort of, rain doesn't happen constantly all the time. It sort of happens every once in a while. But it's pretty neat that we were able to recreate this cloud moderately easily. So then what I did was simulate an atmosphere that had very clean air, very relatively few aerosols. So I changed the initial amount of aerosols. And what happened was there was an increase in liquid water content and a decrease in the amount of droplets. So if we think back to the lifetime effect, you have less droplets and more water on per droplet, you'll get more rain. And that's exactly what we see in this third plot right here. So on the other side, I simulated very polluted, let's just say there's lots of pollution that comes from Boston and mixes in with this air mass. We see that there's a decrease in liquid water content, an increase in the amount of droplets, again from the light jump effect. This led to less rain. What you can also do is make the precipitation a function of cloud droplet number concentration and liquid water path. I fit this plane to about a few tens of thousands of data points. And again, you can see the light jump effect.